Hi there. All right, grade 10s. Okay, in this video, we're going to be talking about impulse. Now, impulse relates to kind of all of the previous topics we've talked about, relates to force, relates to time, relates to momentum. So, in our last lesson, when we learned about momentum is essentially the quantity of motion. It's a way of measuring the motion of an object. And it relates to the mass and the velocity of an object. If an object has no velocity, it has no momentum. And as it gains mass or gains velocity, the momentum increases. Now, how does that relate to impulse? Impulse is defined as the change in momentum. It's essentially a measure of how much the force applied to an object then changes the momentum of the object. Okay, so let's just kind of put this all together. We know when we learned about force that in order to change the motion of an object, we need to apply an unbalanced force. Okay, now when we apply that unbalanced force, we are changing the velocity of the object. And we know when we change the velocity of an object, any object that has mass, we are changing the object's momentum. So we have many things coming together here. Force, velocity, momentum, they're all kind of closely related here. So impulse, again, is defined as the change in momentum, and it's going to depend on the force applied and the time over which that force was acting on that object. So there's a few different formulas that all relate to impulse here because force, time, and momentum and impulse, they're all very closely related here, okay? So one thing we need to kind of keep in mind here is essentially the formula that derives itself from the definition, okay? J is actually the symbol for impulse, and impulse is equal to the change in momentum of an object. If we remember before, this is that delta symbol. That stands for change in, and P is momentum. Okay, but in order to change the momentum of an object, we know we need to apply a force over a certain time period. So that mathematical relationship can also be shown using this formula, where impulse is equal to the force multiplied by the change in time. Okay, so where the impulse is going to be related to how much force you apply to that object and over what time interval. Okay, I'm going to be showing you a video where somebody throws an egg at a wall or at a bed sheet, and you'll see the relationship between force, time, and impulse. So make sure you pay attention to that. It's about 1 minute long. Now, our units for impulse can actually be in two different units because impulse can also be calculated using this formula, where impulse equals PF minus PI, where PF is final momentum and PI is initial momentum. Therefore, whenever we're calculating that, we're calculating a change. So again, that relates to that initial formula from the last slide. Okay. Now, because impulse relates to change in momentum, and our units for momentum are kilograms meters per second, there are two possible units for for impulse, okay, because it relates to momentum as well. All right, so let's walk ourselves through a couple examples here, but understanding there are a few different ways to arrive at an impulse calculation depending on the information you've been given. All right, you kind of have this, where impulse is force times time. You have where impulse is equal to final minus initial momentum, and that relates to the idea that impulse is equal to that change in momentum. All right, so example number 1. A hockey puck strikes a goalie's mask. The time interval of the impact with the mask is 0.012 seconds. During which the mask exerts a force of 400 newtons in order to change the momentum of the puck to 0. Determine the impulse provided by the mask on the puck. Okay, so what's happening here was somebody shot the puck. It's flying at the goalie's mask. Therefore, the puck had momentum. And then the mask essentially had to provide an impulse to change the momentum of the puck to 0. Okay, all right, so in this case, we're going to be using impulse equals force times time, where impulse is equal to 400 newtons times 0.012 seconds. And that's going to equal 4.8, and in this case, my units become Newton seconds. So the goalie's mask had to provide an impulse of 4.8 newtons per second in order to stop the momentum of the puck. Okay. Now, if you were looking at this, you could actually also indicate that impulse would have been negative if you were referring to the motion of the puck as the forward direction, but we don't really have any guide here. But just keep in mind, impulse is a vector, so the direction of the force would actually equal the direction of the impulse. All right, another example. An object has a momentum of 1,000 kilograms meters per second. What impulse is required to bring it to a stop? How much force is needed if it stops in 1 second, and how much force is required if it stops in 4 seconds? All right, so what we have to think here is we know that impulse is equal to final minus initial momentum, right? Because impulse is equal to change in momentum. If an object has an initial momentum of 1,000 kilograms meters per second, and we're bringing it to a stop would mean final velocity is 0. And if final velocity is 0, final momentum is 0. Okay, so how we have to treat this is this 1,000 kilograms meters per second is my initial momentum. My final momentum is 0. Therefore, in order to calculate my impulse, I go final minus initial, which means my impulse is actually negative 1,000 kilograms meters per second. And I could leave it in that units, or I could write it as Newton seconds. Okay, so that's my first step, is kind of essentially converting that momentum into an impulse, all right, based on this understanding that impulse is equal to change in momentum. Now, how much force is needed if it stops in 1 second? So now I have to jump that impulse value into the other formula, where impulse is equal to force times time. All right, now I have my impulse from the previous part. So now negative 1,000 kilograms meters per second, or actually I'm going to just jump that to Newton seconds in order to get it into force. I'm solving for force and I have 1 second. All right, so I do that algebra, divide by 1 second on either side, where now force is equal to negative 1,000 newtons. And again, where that negative is referring to the direction, right? Because in order to stop something, the force needs to be applied in the opposite direction that it is working in, okay? Now, how much force is required to stop it in 4 seconds? So we essentially just go back, but we change the time. Okay, so now I'm dividing by 4, where now force is equal to negative 250 newtons. So let's kind of think a little bit carefully about what happened here. As our problems between kind of the third and fourth segment here, as we increased the time, we decreased the force, right? When when the time was 1 second, the force was 1,000 newtons. And as the time was 4 seconds, the force was 250 newtons. So this is an important concept with impulse, and we use this in sports, we use this in safety equipment. The impulse to the object actually cannot change, right? If an object is moving and it has an initial velocity, and let's say it's going to be stopped eventually, no matter how you get that change in momentum, the impulse will always be the same. But what you can change to the object is potentially how much force is going to occur. So by increasing the time over with which the force applied, the force can be decreased. All right, so you're gonna have to read your notes on this, but let me just explain how this would maybe apply to car safety. All right, let's say for example, and I know, sorry, I'm going on a bit of a rant here. Let's say for example, you're driving your car and you get in an accident. All right, your car slams into a concrete barrier. The time of impact is going to be so low that the force to your car is going to be very high. Okay, small time, high force. High force typically equals a lot of injury. Now, let's say that same car was traveling at the same speed, and instead of running into a concrete barrier, you ran into like a phys ed crash mat. All right, that phys ed crash mat, the car is going to stop in a longer amount of time, right? Because it's going to kind of give into the crash mat. By increasing the time of impact, you will actually decrease the force to the car and thereby to the passenger. But in both scenarios, the impulse would have been the same because the initial and final momentum would have been still the same if the car was traveling at the same speed in both scenarios. So what you have to consider is that you can't necessarily change the impulse, but you can change the time of impact, which has implications in both sports and safety equipment, which you'll be reading about next. All right, last example. In a car collision, a large 1,400 kilogram sedan rear-ended another smaller car. The sedan was traveling at 13 meters per second before the collision, and 0.47 seconds later, it was traveling at 6 meters per second. Calculate the impulse using the formula where J equals Ft. All right, so, you know what, I'm okay with that. All right, so there's more than one formula for impulse. If we're forced to use this formula, let's see what we have. Okay, we don't have impulse, so that's a bit of a problem. Do we know the force in this question? No, we actually don't. We have a time, we have a mass, we have an initial velocity, and we have a final velocity. Okay, what we need in order to be able to do this formula is really to calculate force. Okay, we know force is equal to mass times acceleration. Okay, we have mass, but we don't have acceleration. Okay, what do we need to calculate acceleration? We need final minus initial velocity over time. We actually have all of those factors. So this is a fairly high level question, okay, where we have to piece together multiple things in order to finally arrive at the answer. But we have all the information, it's just going to take some steps. So the hint here was you have to calculate acceleration and force first, which we will. All right, so step one, using this formula, I calculate acceleration. 6 meters per second, subtract 13 meters per second, divided by 0.470 seconds. So acceleration is negative 14.4 0.8936, and I'm going to kind of save the rest of the unit numbers. All right, so I know my acceleration. The negative is implying that the vehicle is slowing down in this case. Okay, from here, I now can calculate force. Force is mass times acceleration. I have my initial mass, 1,400 kilograms, and I'm now going to multiply that by my new acceleration. Now, because this is a multi-step problem, I am going to actually save all of the digits in my calculator and then multiply it by 1,400, which gives me negative 20,851.06. And I'll leave it at that. Okay, now, this is a big problem here. Now I can calculate impulse. Sorry, I'm kind of running out of room. Impulse is force times time. I now have my new force, negative 20,851.06, and I would save that in my calculator, times 0.470 seconds. Again, using all of the information that the problem gave me. Final answer, impulse equals negative 9,800 Newton seconds. And it actually works out exactly. Okay, so let's keep this in mind. With all of that work, we were able to arrive here. Okay, it took us a lot to get there, but we were able to do it using the formula impulse equals force times time. Now let's try that same problem, but with a different approach. The same car collision, okay, all the same values, but now we're going to use this formula, all right? Based on the concept that impulse is equal to change in momentum, we will use final minus initial momentum. So now we have to think, well, how do we calculate final and initial momentum? So this is where we need to think momentum is mass times velocity. So this is how I'm going to show this, okay? Impulse is going to be equal to mass times final velocity minus mass times initial velocity. Okay, all I've done is I've expanded the final minus initial momentum and subbed in my momentum equation. Okay, all right, so mass is 1,400 kilograms times final velocity is 6 meters per second minus 1,400 kilograms times 13 meters per second. Now you don't have to do this all in one step. You could have solved for final and initial momentum somewhat separately. All right, so it is important to use those brackets and to calculate those values kind of separately. So if I multiply these two numbers together, I get 8,400 kilograms meters per second, and I'm subtracting 18,200 kilograms meters per second. Last step would be to do that subtraction, and you end up getting negative 9,800 kilograms meters per second. So if we look back to our last problem, we have the same answer, okay? So two different approaches to get yourself to the same answer, and impulse can have either form of units. All right, I know that was a lot. Hopefully you followed along, fill in your notes. You're going to be completing some questions in your workbook, and then you will be kind of reading the rest of the notes a little bit by yourself.